Thank you for calling on down and getting your notes. Technically, we probably should be doing right now grading of section 4.1, but because it's chapel day, number one, so we have less time. Number two, because we did not get to go over word problem examples on Friday. Hopefully you guys got a good start. Does anybody have a place where they kind of got stuck because of word problems? Some of you I know power through that, like you go work on examples, look at examples. But did anybody get stuck around the word problems and you're willing to share where that was?
Like 57.
50, in the 50s, 60s? Okay. So in the late 50s, 60s, not the 1900s, but in the late 50s, 60s of homework might have been where you got stuck. So I figured, let me go ahead and end the recording. And with you guys right now, let's do 2 word problem examples real fast instead of grading 4.1. That way you can go peek at those word problems because I think they're going to be pretty similar. And then tomorrow we'll grade with you guys having had all the information. Now, the one thing that I'm not having on the screen for very long is degrees, minutes, seconds. So let's talk about that really quickly first, then word problems, then we're getting into section 4.2. Instead of grading, and we'll grade tomorrow because it's a minute. Okay? So notes open. Here we go. Degrees, minutes, seconds. Do you guys remember why on earth? Why on earth? That might be a hint. We might split a degree into tinier sections because 1 degree is so small. Why on earth do we split it up?
Earth is so big.
Earth is so big and spherical. If you think about the longitudes, the ones that go from the North Pole to the South Pole, all the way around, 1 degree, that entire circumference of the Earth cut into 360 degrees. Well, 1 degree sure covers a lot of space.
Oh, yeah.
And so if we want to get zeroed down more, we got to cut that degree into pieces. Now, if I was to draw a circle on the board, could I show you minutes? I can barely show you a degree. How can I show you minutes? But if I were to go out in the ocean and be like, hey, from here to like this mile marker over there is 1 degree. And then let's cut that into 60. Okay, then it would make more sense. But guys, we don't just cut a degree into 60 pieces. We also take a minute. Remember, this is not time, but time helps you remember the 60. We can take 1 minute and cut him into 60 pieces. Once again, trying to get as precise as possible. Now, what if we're given degrees, minutes, seconds? Can anyone explain to me how I took degrees, minutes, seconds and made them all just degrees? How did I do that? I did it quick on that. Yeah, Joel.
Didn't you put it over minutes and then seconds?
Good. I put 14 minutes over how many minutes is in a degree? 60. And then I took 10 seconds and put 10 over how many seconds is in a degree? 3,600. Now, could I build bridges and show you the exact same thing? Mm-hmm. Yeah. Because we could have taken, how many degrees were in the first one? 14. Sorry, 14 minutes. I could have multiplied by 1 degree, 60 minutes. Do you guys see how it would end up being 14 over 60 degrees? Build bridges to get rid of what we don't want. That's why I'm dividing it by 60. What if I had the second one? How many seconds? 10. There are a couple choices on this one. You could have thought, well, I need to get 60 seconds into 1 minute. We could have done that conversion, but would that have gotten me all the way to degree? Don't just the seconds cancel?
Yes.
I still have minutes?
Yes.
So what would I have to do to get all the way to degrees? Go again, right?
Oh.
Dimensional analysis, Ken, Mrs. Leon, building bridges, get rid of what we don't want. To get rid of the seconds. You could have gone to minutes first and then to degrees. But guys, what did I say up on the board? How many seconds are in 1 degree? What else could we have done?
60.
We could have just divided by 3,600 and not had to go to minutes first. We could have skipped all the way and said, hey, 1 degree is just 3,600 seconds. And wouldn't we have gotten 10 over 3,600? Right? Okay. Yeah, that one is kind of easy. The second one's a little bit harder. Now we're going from a decimal 2 degrees, minutes, seconds. So this one was pretty easy. But still, let's talk about the strategy. Where did the 14 go in my dimensional analysis or my building bridges? Why isn't he there? He's a whole degree. I just get to put him in the degree column or in the degree section. So I just take the 14 degrees, that's good. I only take the fractional degree because minutes and seconds are only good for cutting up degrees. So I take the fractional or the decimal degree and I multiply him by 60 minutes over 1 degree, multiplying, there's my bridge, gotta get rid of the degrees. When I multiplied, it was 21 and I was done. 21 minutes, there's no fractional pieces left, so 0 seconds. But what was different in this example? Where'd the 7 go? It's a whole number. So 7 is how many whole degrees? I use minutes and seconds. Michael, stop the tracking machine. I just need to take the fractional degree, 0.365. I need to build a bridge, so I multiply by 60 minutes over 1 degree. It's like 12 feet over 1 foot. Sorry, 12 inches over 1 foot. 3 feet over 1 yard. You just multiply by something that's equivalent from our table up above. What happens to the degrees when I multiply? Good, the degrees cancel. That's the whole point, right? What's the unit I have left?
Seconds.
Close. Minutes. 1 tick mark. Seconds or 2. I multiplied, but guys, why did I only put 21 in my minutes? 21 is how many whole minutes. I have something smaller I can cut it up into. I need fractional minutes. So the same way I took the decimal of the degrees and converted him, I'm going to take the decimal of the minutes and convert him also. So 0.9 times 60 seconds over 1 minute. What happens to the minutes? They cancel. I have seconds left over. What's 0.9 times 60? 54, and I'm done. 54, and I'm done. So degrees, minutes, seconds, there are 2 examples. I did talk through it a little bit slower on Friday, but we didn't get to finish that last example, hence why I wanted you guys to see me work it out right there. Okay, let's get back to our word problems. The one big thing I told you guys on Friday was, for all of these applications, theta needs to be measured in radians. If it's not in radians, we're in trouble. So number 64, angular and linear speeds. Okay, fine, we have formulas over there. Let's try to figure out how on earth to use them. The carousel width, what are we given? How would you guys write this down if you were trying to shorten it but still get all the important information when you write your problems and directions in homework? Good. We could say given d, which is the diameter, is 50 feet. What else do we say? Yeah, we could say 4 RPM. Revolutions per minute. Maybe you guys know RPM, what that actually stands for. Anyway, another way of looking at that is 4 revolutions per minute. Letter A asks for what? And according to over there, angular speed, that would be our omega, is equal to, now they even tell us the units they want, radians per minute. What do we already have? Revolutions per minute. Well, if we want to go from revolutions to radians, we could go over here and look at the formula, but they didn't really give us a theta. They didn't give us like, oh, it goes halfway, it goes a fourth of the way. They didn't give us like a certain angle. So maybe we're just supposed to use the RPM and somehow convert the units. So kiddos, what if we were to take the 4 revolutions per minute? Do I need to get rid of the minutes? He's fine. But what do I need to get rid of? I need to get rid of revolutions. I need to do something with revolutions down here. And what do I need to get into it? Radians. I like to ask ourselves the question, how many radians are in 1 revolution, or how many revolutions are in 1 radian? Which one makes more sense? I heard it.
2 radians or 1 radian.
Close. 1 full revolution, not 2 radians. 2 pi radians. Does that make sense? Because 2 would have just been like 1, 2, that's like in the second quadrant somewhere. 2 pi radians, though, is 1 full revolution around a circle. So we can actually multiplied by 2 pi radians is 1 full revolution. And we didn't even have to use our formula, we just got to use dimensional analysis, and we end up with how many radians per minute? 8 pi. So for letter A, since they already gave me a something per minute, I just had to change it to be what I wanted. Using 2 pi radians and 1 full time around the circle. Now, in letter B, what are they asking for?
Linear speed.
Yeah, linear speed. Over there, that would be, what does the V stand for? Is that rho? No. You guys looked it up, did it? Who has a Greek alphabet close? What's the little V? You didn't write it down. Oh, bummer. We didn't write down all the physicsy ones. Oh, new. That's what it is. Anyway. Okay. Feet per minute. Stink. Feet per minute. We gotta get feet in there somehow? Maybe we should go look at the formula, because I don't know how to get feet in there. Revolution and radians, they were really related, but how do we get feet? Well, okay, the formula for linear speed says S over T, or R times theta over T. And guys, who's theta over T? Who's that the same thing as? I can actually just take omega. I can actually just take the angular speed and multiply it by radius. So there are a couple different ways of looking at the formulas. Maybe it's good to get that down in your formulas. It could be S over T if we knew the arc length. Or it could be S is R times theta over T. Or it could be R times who theta over T is, which is omega. Or angular speed, which means, well, if we already have 1, if we already have omega, what can we do? My microphone might have stopped working. We'll see if I got it working or not. I know you guys saw it last year. How many of you guys had unit circle quizzes? I know you did.
Yeah.
How many of you for those unit circle quizzes just kept on like trying to memorize everything on it? How many of you guys found patterns to help you with your study? How many of you guys right now could use what you learned, memorized last year, maybe learned, to answer something right now like sine of 7 pi over 6?
No, I do not have it.
No, I should ask the hands. Who thinks they have it?
It's not.
I did not know.
It's not happening.
So how many of you guys, do you think it was more of a short-term memorizing thing?
Short.
Yes.
It's always short.
I memorized completely.
After that, we never talked about it until the final. It was like,
Yeah, it was like, yeah, this is the unit circle. You don't need it right
Question, what's 6 times 100?
660.
What did you guys just think about? Did you literally think about 100 different things and then 6 different sets of them and then add them all up?
Yes, ma'am.
You had a pattern and it stuck. Now, you've had how many years to get that pattern down?
A lot.
A lot. What's 7 times 9? I had fewer on that. What's 11 times 12?
11.
1.
No,
Is that what?
that's 121.
Let me get my calculator.
So, some multiplication. Alright. Some multiplication is harder than others. Some multiplication is harder than others, right? Doesn't mean we can't do it, just means...
132.
That's what I got.
Okay. Long story short, if I can somehow attach the unit circle and help you guys understand how it works instead of just maybe how it works. Yeah, how it works. Instead of just like, hey, it's important to memorize it. Maybe you'll remember it longer, which is important because for the SAT, the unit circle is on it.
What?
For, just a little bit, not a lot. For any math placement test into college, unit circle will be on it.
Nope. Oh, okay.
In calculus, you have to, or else they will take you.
Darn.
4. You guys have to be a math person, so that's cute. Coming back. 4. Any calculus class, you're going to need to know it. For a math placement test, that bumps you back to geometry. You're going to have a lot of unit circles. You're going to have it in algebra 2 and in pre-calc.
You're going to bump me back to
If
geometry?
you don't pass the math placement test.
Oh, no.
Not necessarily. It's something called college algebra, and they might not teach you. Long story short, if I can help you get a better understanding of how it works, hopefully it will stick in your heads a little bit easier. So, first of all, how many of you guys would call yourselves visual learners? Usually visual learners kind of like geometry. So it's like, I can see it, I can see the triangle, I can see the parallel lines, not everything, maybe not proofs. Okay. How many of you guys, hold on, are just like, I can memorize. If you just give me something to memorize it, I'll memorize it for as long as I need it. Okay. Memorizing people, there's something called the cheater chart. Visual people, there's something called triangles. And for some of you that are like weirdly a little bit of both, you just choose what you want after I show you
Look at
both.
none of those.
Okay, none of those?
Algebraically, I can do math.
Algebraically would kind of be like, find the pattern, you know. And you technically are one of those where you can choose either one. Okay, here we go. Ready? In the unit circle, there are these little things called points. With an X and with a Y. An example of points would be root 2 over 2, comma, root 2 over 2. Or 1/2, comma, root 3 over 2. Or 1, comma, 0. Those points in the unit circle last year had an X and had a Y. Now, a couple things to talk about for a circle. First of all, the normal equation of a circle, centered at 0, 0, would be x minus 0 squared plus y minus 0 squared equals r squared. But a unit circle is called the unit circle because we scale everything back to where r, the radius, is just 1. R, the radius, is just 1. So even though we could say r squared, we're going to say 1 because it's 1 squared in a unit circle. So I'm going to mark right now the hypotenuse, wait, what? A triangle. The hypotenuse to be 1. I'm going to mark the hypotenuse to be 1. Now, to get to this point, you go over an x and up a y. So technically, in the unit circle, any point can just be a triangle. Technically, in the unit circle, any point can just be a triangle, where you go over an x and up a y. Now, if you guys remember SOHCAHTOA, maybe this makes a little more sense as to what? Wait. As to why, so. S-O-H, what does that mean? Sine.
Over hypotenuse.
Opposite over hypotenuse. So look at our triangle. Which one of these has to go to sine if it's opposite over hypotenuse?
Y.
Yeah. So of course the sine of an angle is going to be the y value. Because if I was to draw a baby triangle at that point, at that angle, his opposite would be the y and his hypotenuse would be 1. Always is in the unit circle. Now guys, what would the x have to be then? Well, adjacent over hypotenuse is which trig function?
Cosine.
Cosine. Now technically we're not really reviewing SOHCAHTOA until section 4.3. But for those of you that liked geometry, visualizing, technically, if you can make a little baby triangle with every angle and figure out what the x and y and the hypotenuse are, you can just think of SOHCAHTOA and it will help you out as far as which one's which. Basically, the coordinates, the x and y of any point on the unit circle relates to or coordinates with trigonometric ratios. Or we could also say values. Trigonometric ratios, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So I'm going to show you how to think about the unit circle with triangles. Tomorrow I'm going to show you how to think about the unit circle a couple different ways. We're actually spending a few days on the unit circle. Today and tomorrow for sure, maybe another day as well. We have a big unit circle quiz coming. We're going to have some like really impromptu candy unit circle, like just seeing if people can get it at the beginning of class. One's coming. It's going to be important to memorize it, but I'm going to try and show you a few different ways. Don't automatically go home tonight and just start like writing down or printing out and just like memorize. Maybe that's the way that worked for you last year, maybe, for my memorizing ones, maybe, but give me a chance to show you a couple different ways of thinking about it. First of all, let's pause for a second. So what can we say? From the coordinate, from the x and y of every point on the unit circle, we can say the following. Sine of t, I'm going to draw a quick little t is an angle. If you like theta better, you can write theta instead of t. T is just an angle. So sine of t, or sine of an angle, is going to be the y value. Because it's opposite over hypotenuse. Cosine is going to be the x because it's adjacent over hypotenuse. Tangent is going to be y over x as long as x is not 0. If it is, it's just dn. Because tangent is opposite over adjacent. So let me give you a second to write these down. But as you do, let me get that little triangle back for any x, y. In the unit circle. You could memorize these little formulas, or you could review right now. SOHCAHTOA, and I heard that Mr. Che stole this. I don't know if he stole it or if he just thought of it. SOHCAHTOA. SOHCAHTOA. Sounds like a Indian princess or something. And SOHCAHTOA sounds like an Asian princess. I'm just making that up. I don't know, it's just a way of remembering. SOHCAHTOA. I was thinking Native American. Mostly. I'm not sure if SOHCAHTOA actually sounds Indian. don't think it does.
What is it?
Neither of them there?
I'm sick.
I'm done. So if you want to review SOHCAHTOA CHOA you can look up there and say sine, opposite, over hypotenuse, y. Cosine, adjacent, over hypotenuse, x. Tangent, opposite, over adjacent, y over x. Cho, if you guys have never heard that before, Cho is cosecant. Hypotenuse over opposite. Cosecant flips sine. 1 over y. Secant flips cosine. Hypotenuse over adjacent. 1 over x, sorry. Cotangent flips tangent. Adjacent over opposite. So some of you are just strict memorizing. Maybe these formulas will be helpful. For those of you that are kind of more visual, maybe using the triangle and remembering something like SOHCAHTOA CHOA could help. Both secant and tangent, if we were to find them up here, both secant and tangent have x in the denominator, which means they're both going to be, we're just going to call them undefined, or we could say DNE if we want. Undefined or DNE when x equals 0, which is going to happen. X equals 0. Well, x equals 0 on the y-axis, right? On the y-axis, we have the angles 1/2 of pi, 1/2 of calzone, and 1.5 of pi, 3/2 of pi. 1.5 calzones. Cosecant and cotangent, if we look at those derivatives, they both have y's, derivatives, wrong class. Those denominators, mostly I know. That happens when y equals 0. And that's going to happen on the x-axis when t equals 0 and pi. Now, for those of you that kind of like geometry or kind of see themselves as a visual type of person, back in geometry there were 2 special types of triangles with certain angles where you could know the ratios of their sides. One was a 30-60-90. And another was a 45-45, right? You might need to review them. But the entire unit circle, all the pi over 4s, pi over 6s, pi over 3s, and all their multiples are built on those 2 triangles. If I can get to switch the page. Struggle. Come on, buddy. You guys ever find yourselves like sweet talking your devices? Let's go. Come on. Oh dear. You threaten. As long as you don't hit it, that doesn't always work so well. The entire unit circle is built on these special triangles. The entire unit circle is built on these special triangles. Now, I'm not going to go through and show like all the x's, like the 1x, the 2x, the root 3x, and I have like talked about that in geometry. But what I am going to show you is the ratio of sides, which ended up being, for 30-60-90, 1, 2, and root 3. For 45-45, like x, 2x, and root 3x, that's kind of maybe what you learned once upon a time. For 45-45, it was 1, 1, root 2. You could check 1 squared plus 1 squared is root 2 squared, it works. And for 60, well that's just a 60-30, but flipped on end. So it's the exact same thing, except the 1 is down here now. The root 3 is here now, and the hypotenuse is here now. Now kiddos, we talked about how to go from degrees to radians. So if we were to take this 30 degree, which is 1/3 of 90, or 1/6 of 180, that's the same thing as pi over 6. 45 is the same thing as 1/2 of 90, or 1/4 of 180, which is pi over 4. And this last one is pi over 3. I know people got out early, and I'm watching the fun. If you're a visual type person, for any over 6, 1 pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, any over 6, you can use this triangle. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. You can use this triangle to find your sine, cosine, tangent, cosecant, secant, cotangent. The only thing you need to figure out is how to do the signs. How to do the positive or negative. I heard that Mr. Che has already learned all students take calculus. I heard Mr. Parks doesn't know what that means. Well, he teaches them. Tomorrow we'll try to figure out. But guys, any over 4, we'll use this triangle. Any over 3, we'll use this one.
Yeah.
And we'll see how we can visualize and solidify the unit circle tomorrow. Finish out your 4.1 tonight. Have a great day. The brave, the few, the proud can try for 2 to start it. Don't be afraid for it. Challenge accepted. Give me a chance. Change how you study the unit circle.
If it works.
Give me a chance to improve how you learn the unit circle.
I'm just like, hey,